Okay, and that is just a rectangular bar with 10 into 10 millimeter of dimension, and it has usually it has a V notch, it can have a U notch, it can have a key hole kind of notch, and this dimension is 55 millimeters. All of them are in millimeter, and then you have a hammer. Okay, so you have a hammer of fixed weight which is at a fixed height, and then you put your sample here. Okay, and if the hammer falls and there is no specimen, then it will attain certain height. Okay, because of the potential energy it has gained because you have elevated it to a height. If you have a sample, then it will break the sample and certain amount of energy will be consumed in breaking of that sample. Okay, so it will not attain that height, it will go to some different height, and this difference will be the amount of energy which is absorbed in initiation of a crack and propagation of a crack. So remember, it is not a sharp crack, it's a notch in this case, and the energy will also go in creation of sound and heat. Okay, but those energies are less in comparison to whatever energy is required to break the specimen, so we ignore that. And this difference in energy is mechanically inbuilt in the machine, so that there is a needle which shows on the dial how much energy is absorbed for the specimen whenever you break it. You can have digital forms also where you get a value on a digital screen. And so this is the test which, so I think it is E23 ASTM, which is the standard for this. And this is the test which is used by the industry for finding out what is the, so in the operational temperature, if you have a possibility of brittle fracture or not, so you do this test at different temperatures, and then you plot the Charpy energy. CV, because C is Charpy, V is V notch. Okay, and for VCC you will get a huge scatter, and then you fit it in sigmoidal curve, and then you either you take the average at different temperatures and you plot the average values, or you take all the values and fit it in a sigmoidal curve and you get this kind of curve. So this axis is temperature. So when you go higher than certain temperature, then it attains a plateau and it will not increase beyond that value. That is called upper shelf. Lower shelf for certain materials can be attained at -20, 0, depends. So the same steel which is breaking at 300 joules at room temperature will break at 4 to 6 joules at -196, which is the temperature of liquid nitrogen. So you can actually break it with your hand, but don't try it because it will be very cold. And so in lower shelf you don't have much scatter, upper shelf you don't have much scatter. And the value or temperature below which you think or you can see from the data that there is no no ductility at all, not significant amount of ductility, that temperature is called negative or nil ductility temperature, NDT. Okay, and the median, so lower shelf and upper shelf and middle point of that will be describing 50% chances of ductile or brittle, so that is called DBTT, ductile brittle transition temperature. And when you break these samples on the broken surface, you will see, as I said, that so initially if you cut the sample, then you will have a notch region, and then you have this flat region. Usually this notch is 2 millimeter deep, so this is 8 millimeter, and this is the broken piece. So here you have 10 cross 10, and this is half of 55. The total length is 55, half of that. And so the hammer should hit from the back side, so this is a 3-point bend at high velocity. And when you break it, then you will see that this will go in. like this because of the constraint which we have spoken about. And constraint will change as the ductility of the material changes. So if you go higher in temperature, then this sinking will be more. So this can also be measured in the form of a crude form of a strain. Okay. So the initial, whatever you call it, thickness T naught was the initial thickness, which was 10 millimeter, and then there is a negative. So because there is a compression, so here the thickness is lesser than 10 millimeter. So that you measure. So suppose that is 9.5 millimeter. So then you can calculate a strain which is delta T by T naught, and that is called lateral strain. Okay, and then you can plot this lateral strain also, and that will change with temperature. Okay, apart from that, what you will see because of different, so ductile fracture happens because of void nucleation coalescence growth and coalescence. That is the mechanism. Brittle fracture happens because of micro cracks, and they join each other and then they break in BCC materials. So ductile fracture will happen by plasticity. Also brittle fracture happens with some amount of plasticity to begin with. So plasticity happens on those planes where you have a lot of atoms. So the movement is easier on slip planes. If you have to break something easily, you don't want to break it on the plane where you have a lot of atoms, because you will have to break a lot of bonds. Okay, so you need a plane where you have least number of atoms, so that bond breakage will be less and it will consume less energy. So this is why in brittle fracture the failure happens in BCC on 100 plane. And so what happens is that, suppose this is a polycrystalline material, so you have a lot of grains in it. And each of the grain, how they are different? Why do we have a grain boundary? Because the orientation of each grain is different. So in each grain you will have 100 plane in a different direction. Okay. So this grain is breaking on this plane, and then in the next grain that plane is at a different direction. So what will happen is that this plane will break, that plane will break, and these two will have to join now. Okay, so the intact part will break after some time, after the failure on the least packed plane. So on the fracture surface you will see some features which will be an elevation in the height. Okay, so you have one plane in one of the grain which is breaking, suppose in this direction, another plane has broken in this direction, and then there is a step formation. Okay, so this is called a tongue kind of feature. Okay, and then we'll talk about fractographic details when we talk about fractography. So you can look at SEM and you can see different features which can also give you an indication of the fracture toughness of the material. So that we'll discuss when we discuss about quantitative fractography. Okay, there will be a little bit of stretching here because it will blunt a little bit, because it's not a sharp crack. Even if you have a sharp crack, it will blunt. Depends at which temperature you are testing it. So if you don't really have a ductile tearing but only blunting, then that parameter also can give you the estimation of the transition temperature. This is called stretch zone width. Not much work is done in this area, but a lot of work is done on reactor pressure vessel steels in ductile to brittle transition temperature. So, and then you can also do fracture toughness testing with this specimen with the same apparatus. What you have to do is, for fracture testing, you need to measure displacement and force both. That is what you get in UTM when you do at quasi-static loading. In Charpy test, you don't get any value except energy. Okay, so you will have to put a strain gauge on the hammer, and you will have to, so that strain gauge will give you the value of forces, and those forces will be oscillating because it is at higher velocity. Okay, so the force profile with respect to time you will get, and it will go something like this. And from this time, you have to estimate the amount of displacement which might have happened, or you integrate the area under load versus time curve and estimate the value of energy. And that kind of testing is called pre-crack Charpy V-notch testing for fracture toughness. Okay, so you can calculate another parameter which we will discuss using the Charpy impact test equipment, but you have to make it instrumentized. So you have to do some instrumentation for putting strain gauge and other things. You don't put the strain gauge on the sample because at lower temperature you are putting it at liquid nitrogen, so strain gauge will not work. And when the sample breaks, the hammer will hit, so strain gauge will obviously not work. So you don't put it there. Okay. So if you look at, and we have seen that those kind of data. So this example is there. What happened? I don't know. Is it connected? So if you look at this data, you have, so here there is another variable which is written as K1R, okay, or K1I also you can see, K1A. Okay, so these are the values which you get from different testing. So K1A is called the crack arrest fracture toughness or stress intensity factor, which is calculated by not propagating the crack but arresting the crack. Okay, and K1R is calculated. I'm not too sure about K1R. I am not so sure. It might be the value of K1 which intersects with the R curve, or it might be a K which is calculated from the Charpy test. I'm not too sure about it, but this is a similar parameter. So the same behavior you will get if you plot Charpy also. The behavior is going to be same if you plot Charpy energy on y-axis. And you see that the tests are done for one material. This is one material, but they have been done at different thickness. So you have 1 T, T meaning T is thickness, 1 T means 1 inch. Okay, so 0.5 T will be half inch, 1 inch, 2 inch. People don't go beyond 2 inch because for a steel that is already too much. So you see different symbols, circles and squares and open circles and triangles. And you see for different temperatures you have a huge scatter. Then there is a conservative approach which says that you take the lower bound, and so that's the worst case. Okay, so you take the lower bound connecting the lowest value of all and try to be in that region so that your material is safe, but that is over conservative. Okay, it's like hitting nil probability of brittle fracture. But you don't want to do that because if you are that conservative, then you will have to discard a lot of materials. Okay, so this data looks very scattered, right? And then you apply some median statistical approach, and the same data using master curve is shown here. So all the same data. And when you do master curve analysis, which we have discussed, and plot KJC or K1C or K1R versus T minus T naught, you remember T naught was a parameter there. Do you remember that? Yes. Yeah. So the KJC was 30 plus 70 exponential. There was C also. 70 into 0.095. Sorry?
95.
95, yeah. And
T minus T.
Exponential of T minus T naught. So T is any test temperature, T naught is the reference transition temperature, meaning at the temperature where KJC values has 63.2% probability of having a value of 100 megapascal root meter. Okay. So this is how the whole statistics is converged in one curve. Okay. So this is the importance of this. And so you see that master curve in upper region of transition. So this is the master curve, the blue one. Okay. So the blue curve, the solid line for the blue curve is representing 50% probability of KJC, and then you have the dashed blue line, which is 95% and 5%. Okay, so this is calculated by valid data because we do censoring. Okay, you remember we did some censoring for maximum likelihood analysis. So for calculation of maximum likelihood parameter, you had to find out. So I is equal to 1 to n, and then you had probability density function, which was del p by del kjc, and then you had survival function, which was exponential of minus kjc minus k naught by k naught, so k min to the power 4, and this to the power 1 minus delta, and delta is 1 if the data is valid, it's 0 if it is not. Okay, so that censoring neglects or censors, not really neglects. So those data are used in the analysis, but those data are replaced with a limit, with a upper limit. Okay, so exact that data which you get from doing the test is not used if delta is equal to 0. So there are different criteria for which you say that the test was not valid to be counted in the statistics of ductile to brittle transition. There are different parameters. One parameter is that if you have a ductile tearing of greater than 0.2 millimeter, then you can't take that data so you can't assume that data to be valid. So you assign delta is equal to 0 to that. When you assign delta is equal to 0 to that, then you take an upper value of kjc and replace the experimental data. So suppose your experimental kjc was 297 megapascal root meter, and then you calculate the limit of kjc which you will get for that temperature using the yield strength and other values. You get an upper limit by calculation following some theory, and that comes out to be 250. If delta A is more than 0.2, then you replace this with 250 and then you assign delta is equal to 0. Okay, so you will have to create a lot of data, and the problem is that suppose you did 200 tests and all of them are invalid. Okay, so people who have discovered this methodology, they argue that we are not really neglecting the data, we are just censoring it. But the problem is that if all the data is censored, then you can't get a value. With all delta is equal to 0, you cannot get T naught from MLA. Okay, so and the probability of getting a lot of invalid data increases when you decrease the size of the specimen. And the next thing is, if you do a lot of testing at upper region of the transition temperature. So this is the transition regime, this and this, in between this is your transition regime. And if you follow master curve, then all the data must be created in this region and all the data here will be censored. Okay, and so if you are doing a test on a smaller specimen, so the idea is that you need to have an estimate again for the KJC before doing the test, so that you don't fall in this region. Because how will you think that at which temperature should I do the test? So suppose you have developed a new material which is very close to reactor pressure vessel steel, and now you want to find out what is the value of T naught. Okay, so then you have to do some testing, and then how will you decide that what should be my test temperature? So for that test temperature, you must have an estimate based from the yield strength and other things, that I have to go in the lower region of the transition temperature where I don't expect a lot of ductile tearing. Okay, and there are other criteria. It's not one criteria which will make it invalid. Okay, there are other criteria which will make them invalid. And so that is that. So what I wanted to show you on this curve is that the blue curve, if you really look at it, it is only taking care of data here. The median is following the median of the data here, and the median is not following the median of these data. Okay, because these data have been generated at in the upper region of temperature. So a lot of data has a lot of ductile tearing. Okay, and if you just plot the valid data, then probably you will see that the median is really following the valid data, but invalid data is also data, it is also a test. Okay, but that thing is not shown by the curve. Okay, so then that is okay. I believe we shouldn't go further with the master curve. So one topic which we need to understand, and we have spoken about it, is constraint. Okay, and one of the parameter for constraint we have discussed. If you remember the stress expansion of Williams equation, what was that? That was k by root over 2 pi r into f of theta, and then you have higher order terms. Okay, so this is c naught, then so except r. Okay, so you can also write it as c naught r to the power minus half f of theta. Okay, then you have c1 r to the power 0 and f of theta, and then you have c1 r to the power half f of theta, and so on. Okay, so this was Williams expansion for stresses at the crack tip. And for Irwin's and also for a lot of work, we only take the first parameter, and we saw that it will not ensure that there are any stresses when r is having a value much larger. So when r is infinity, what happens to this? This becomes 0. So it means there is no stress, but that is not true. So what takes care of that reality are the higher order terms. Okay. So the second term, if you see, there is no r in it. So it's not a function of r, it's only a function of theta. And for theta is equal to 0, we can write sigma ij is equal to k by root over 2 pi r, and f of theta will not be there because we are taking at theta is equal to 0. And then you will have something like this. Okay, and there will be no theta, no r, because r is not there in the second term, and theta we are calculating at 0 degree. So this is how you will get, and T is just a value. Okay, it's a value of stress, and mu is Poisson's ratio. Okay, so you have a stress in y direction in mode 1, and that is causing a stress in the z direction. Okay, with a multiplication of Poisson's ratio, and this is called T stress. And T stress, so this stress is one of the parameters which can tell you how much constraint is there on the material. And this is a normal stress, so this gives you a pressure, this gives you a hydrostatic sigma h. Okay, and this hydrostatic stress can be negative or positive. The assignment which I gave you in last class was to find out for plane strain and plane stress conditions, if you put sigma 1 is equal to n into sigma 2, and sigma 1 is equal to m into sigma 3, and then you put it in the equation of von Mises, what do you get for plane stress and plane strain? Okay, so for plane strain, sigma 3 will be mu into sigma 2 plus sigma 1, and for plane stress, sigma 3 will not be there. So for these two cases, if you calculate then you will see for plane stress, the stress at the tip reaches sigma ys for plane stress. Okay, and for plane strain, what happens is that this thing increases in a very short span of distance, goes to a maximum of 3 sigma naught, 3 times of sigma naught, and then it decreases. Okay, so at crack, exactly at the crack tip, we don't know what really is happening, but in plane strain condition, the stresses at the tip can go as high as 3 times of the yield strength, even though there is plasticity. It can go to that high value. Okay, so this stress is defining that how much hydrostatic stresses are there, and those are not a value of R, so they will be there at the tip also. Okay, so if the value of this stress is positive, T stress is positive, that would mean that you have a hydrostatic tensile constraint. Okay, so that means the material points are expanding. And if it is negative, then that would mean that there is a pressure which is trying to compress it. Okay, so if at the tip you have stress condition which are causing the material points to compress, there is a form of pressure on the tip, then you need to apply more stress to open the crack. Okay, because a part of stress is acting to compress it, and this is a function of geometry. This will not happen, this will happen if you change the temperature, but if everything is fixed, then for different geometries you will get different values of T stresses. Okay, for the same amount of crack length, for the same amount of force applied, width of the specimen is same, A by W is same, everything is same. Just if you change the geometry, then you will have different amount of T stresses. Some of them will be trying to compress the material at the crack front, and therefore you will have to apply more stress, more energy you will need to supply in order to open the crack. Okay, and if it is tensile, then you need less. Okay, so how do we find out what is the value of T stress? How can we find out what is the value of T stress? So the stress at the tip is sigma, and sigma root pi A is K. Okay? So suppose there is a factor which says, so which you can find out, and that is the factor between the T stress and the stress which is there because of the first term. Okay, so let us say that that factor is beta into sigma. So beta into sigma is equal to T stress. Okay, beta is just a factor which is telling you how much higher or lower T is in comparison to the stress which you will get at the tip. Okay, so then I can write it as, so how can I find out beta? So beta will be equal to K divided by T, right?
K.
So K is equal to sigma root pi A. Right? And this will be T.
Beta goes to this.
No. There is something wrong. So sigma we have to put T by beta. So K is equal to T by beta root over pi. Right?
Oh.
So beta will be equal to T by K root over pi A, and K is sigma root pi A. Okay, so this is T by sigma. And if I want to write out in the terms of K, then it will be T root pi A by K. Right? So beta will be T by K root over pi A. Right? So K I can calculate, A I have, T I also I have to calculate. And if I plot beta for different geometries, then I will see that for DE and T specimen and for SE and T specimen, the T stress will be highest, okay, and it will be lowest for 3-point bend specimen. Sorry, it will be lower for 3-point bend specimen. It will be lowest for central crack panel for this kind of crack. Beta is the factor, is the ratio of T stress and the stress which is coming. No, you can plot T also, right? But usually what people do is they usually plot things in normalized way, dimensionless forms. Okay, if you plot T, then you need to know additional parameters like what was the sigma applied, because T will change with sigma. If K is increasing for the same geometry, if K you are applying of 10 megapascal root meter, T stress will have some value, right? Then you apply T, K is equal to 400, T will have a different value, right? So you need to know that information also. So it is better to see the things in the form of a normalized parameter, where you know that if you increase K, then this parameter is going to give you the same value. Whatever is the value of K, whatever is the value of T. Do you understand?
Beta will remain constant for.
Beta will remain because you are calculating T is dependent on K. Sigma ij is equal to K root by R, then you have T. So if you increase K or decrease K, T will increase or decrease. So you can define a parameter which defines the ratio between these two, right? And if you plot it, then you don't need to know how much K is applied.
So I am asking कि हमारे पास beta और T में ही relation है और हमारे दोनों नो
हाँ, इसको प्लॉट करने के लिए तो आपको दोनों निकालना पड़ेगा, लेकिन एक बार निकाल लिया अगर, तो उसके बाद के एनालिसिस के लिए आपको ये बॉदर नहीं करना पड़ेगा कि कितना K था जिसके बीटा की वैल्यू ये थी. If you plot just T stress, you find out T stress and you plot it for different geometries. Okay, so those T stresses will be in the form of absolute values, है ना, 200 megapascal, 100 megapascal, 50 जो भी वैल्यू है उसकी. So then you do not know and you want to ensure कि मेरा T stress का वैल्यू इतना होना चाहिए. K तुम्हारा आ रहा है ऑपरेशनल कंडीशन से, ठीक है. अब ये जो प्लॉट किया तुमने T stress, that might not be at the K where you are going to use your component. कंपोनेंट के साथ वैरी करेगा, तो एक एनालिसिस एक कंपोनेंट के लिए होगी, दूसरी एनालिसिस दूसरे कंपोनेंट के लिए होगी, राइट? So if you do one analysis in the form of a dimensionless parameter, then that analysis can be used for any component calculation. This is why you will see most of the things are plotted dimensionless. Okay. So for example, the distance from the crack tip, in a lot of cases you will see in literature, will be plotted in this form, which will be dimensionless. Not in terms of R, it will be plotted as normalized R. Okay. So if you plot beta, then you will see that for different parameters, for different geometries, the T stress will be different. So for some cases, so what does it mean? It means that if you find out fracture toughness by using 3-point bend specimen, and if you find out fracture toughness by CT specimen, both of them will not be same. Okay, so it's a material property, but it will be geometry dependent. Okay, so you need to ensure even though we have taken care of that all the criteria of ASTM E399 for K1C, that plastic zone should be 50 times smaller than the smallest dimension, all those things we have taken care of. Even then, you will have different value. Both of them are plane strain condition, but in both of the conditions you have different amount of constraints available, and so you will have a different value. So what people found was that if T stress is greater than 0, in that case, the variation in stresses are not that significant. It's like happiness. Okay, you get too much happiness, even then it will not stay for long and it will disappear very fast. No, it's reality.
Yes, sir.
It's a research outcome that if the happy effects which are there on the brain is very less in comparison to the negative effects which you can have. So if you don't like somebody, for example you, okay, and we are walking on the same street and I see you from a distance on the other side, okay, and I had a bad interaction with you, so then I will start feeling some negative thoughts, maybe unhappy or stressed or something, and that effect is larger than an effect of getting a friend which was very good to me and I'm seeing it for like after 20 years or so, not after 20 years because you're old, so 5 years or so, okay, and that happiness will not be larger than the sadness which you can get by so if you quantify the experience, bad experience and good experience, so for the same value of bad and good experience, the effect will be larger for bad experience, unless you do some chemistry with it, okay. So so T stress greater than 0 is a good effect for fracture toughness testing, not for the material. For material is a bad effect because it will break easily, okay. So why T stress greater than 0 is good? So another definition, so there is a term called small scale yielding, SSY. Small scale yielding means you have to make your plastic zone smaller, and why we know, we have discussed, right, because plasticity is cannot be taken care of by the theory of elasticity, so you want to make it ignorable, okay. So small scale yielding, but that's a relative thing. How much is smaller? So Arvind says 50 times smaller, somebody will say 100 times smaller, okay. Depending on your material and your convenience, you might say नहीं उतना नहीं, 20 ठीक है चलेगा. तो इसको कैसे standardize करें, okay. So small scale yielding is defined now when T stress is 0. That's the point of small scale yielding. If it is greater than that, you have more constraint, and if it is lesser than that, you have less constraint, okay. But if you plot sigma y, normalized again, so sigma y divided by sigma naught, and then you plot r sigma divided by j, so that's the distance from the crack tip. If you plot this, then sigma yy by sigma naught will show this kind of curve, okay, and you will really not have values here when r is 0, because finite element analysis cannot take care of, even if it can take care of finite strains, even then there are a lot of things going on at the tip. You have damage and all those things, and damage also, if you incorporate, then also you are not sure what is happening at the tip, so you discard the values here and you can only have the idea there, okay. So this will look like this, and so this is for T stress is equal to 0. If you plot this with respect to, so for T stress less than 0, then the stresses will be smaller and smaller, and this is for T stress. So this also now you have to normalize, so T by sigma naught, this will be negative 0.2, and then negative 0.4, and then negative 0.6, and so on. So this will look like this.
नेगेटिव मतलब
Negative
पॉजिटिव ही होता है सर, नेगेटिव डायरेक्शन अपोजिट होगी, बस ये होता है.
नहीं, negative मतलब compression है.
अगर
Negative, so this you have to look in terms of sigma h, hydrostatic. Okay, so if the summation of all the normal stresses are positive, then you have a hydrostatic stress, and if it is negative, then you have a compressive stress. Okay, so that's the meaning of it. It will not change the direction of sigma y. What is your question?
मेरा क्वेश्चन है मान लें कि t greater than 0.
नहीं, t greater than 0 is good.
Good.
I will tell you how the plot will
तो
look
सर
like.
मतलब greater than 0 मतलब पॉजिटिव डायरेक्शन के हिसाब से या मतलब टेंसाइल में से
Tensile.
में से हो रहा है.
Yes. Yes. So the summation will always be greater than 0. Okay. So for plane stress in that matrix, you will not have mu t. There will be no stress in z direction. So you only have sigma. You only have t. Okay. So if t is positive, then it will look like this. Right? बहुत आसान. But this t is equal to positive is for t by sigma naught is equal to 1. Not for 0.2, 0.4, 0.6, 0.8. So you see the difference. If you reach -1 here in negative, then it will go to a very low value. But a positive stress will not create that much effect in the other direction. Okay. So whatever you do, if you are in positive range of T stress, you are not going to increase the constraint to a very high value. Okay, but negative effects are higher. Okay, so this analysis was done by O'Dowd. I don't know what is the pronunciation. These two guys, and they found that the difference in sigma y and sigma xx, both of them are equal. Okay, so this again proves that the effect is hydrostatic. Okay, and so T stress then becomes a criteria for describing, quantifying the amount of constraint you have at the crack. And the other benefit of T stress is that T stress can be calculated from K values. Or you can also calculate T stress by theoretical means, by putting the equations. And you can also find out T stress by doing line integration. That we will not discuss. Okay, that's a numerical integration scheme from which T stress can be calculated. But remember one thing, if you are modeling something, if you want to calculate T stress by using finite element model, then you cannot use plasticity because it's not a plastic thing. Okay, sigma naught will be there in your calculation for normalizing. And how do we do it? These models, these analyses are done by doing that modified boundary layer modeling scheme. Because you are looking at stresses very close to crack depth, you are not supposed to model CT specimen and 3-point bend specimen and have the effect of gradually decreasing or increasing element sizes away from the tip. Okay, so you take that carved circle at the crack tip and then you ensure that you're at the boundary. So for whatever material you are modeling this, you have to ensure that if you use plasticity, then the plastic zone size will be much smaller. One way of looking at that is that, and another thing what you can ensure is that at the boundary, whatever radius you are taking, suppose you are taking 10 millimeter, so at a distance of 10 millimeter, the stresses must be governed only by elastic theory. So there should not be any plasticity. When that is ensured, then you calculate U and V using those functions. Okay, that was also another assignment. So you calculate U and V, and in that U and V you had, so you kept sigma is equal to, you took that Westergaard's function, no? So sigma z by square root of v square minus a square, right? Then you have to take the second term also, which is T stress. Okay? And then from that you will have to calculate U and V. So if there is a positive term, the net result is going to change. If there is a negative term, then net value of U and V is going to change. Okay? So then you do this analysis for T is equal to minus 0.2, T by sigma naught is equal to minus 0.4, minus 0.6, minus 0.8. Then you model this and then you calculate sigma y along this path. And then you plot it. And then you will see the same thing what they have shown. Is it okay? So remember that T stress is not discovered by O'Dowd and Z. T stress analysis is done by O'Dowd and Z. What they discovered was something else. What they discovered was, so if you again now coming back to Williams expansion, we have first term, then we have a second term, but there are other terms also. Okay? So these people, they define that you will have a stress because of T stress is equal to 0. That is the first term. Or not. Right? So T stress is equal to 0 says that the second term is 0. It doesn't mean that third term is 0. Okay? So then this will be equal to sigma ij and whatever is there, higher order terms. Okay? And then they define that whatever you get as a difference, and then you normalize that by sigma naught, then that is defined as Q. And this is not small q, this is a capital Q because it's different from small q. Okay, so this is what O'Dowd and C described. And they also plotted this with respect to, in comparison to T stress. And T stress and Q, they both show similar behavior. But for higher hardening materials, Q shows a very, very negative value. So it is influenced in a very dramatic way in comparison to T stress. Okay? So it's just another parameter. I don't know if you have remembered, the first parameter is small q, which describes triaxiality. Have we discussed this? Don't remember. So this is just the hydrostatic stress by equivalent stress. That's it. The simplest of all. And this was the first parameter which described constraint. कितना hydrostatic stress है per unit, कितना equivalent, कितना shear stress. Okay. So in a finite element model, you will get one value for one specimen and a particular loading at a distance from the reactor. For T stress also you will get one value. But where will you calculate Q, small q? That small q will be calculated at every point, every node. It will have a different value. Not necessarily. So we know that at crack front, the stresses are going to be different. Okay, so sigma z, if it is going to be like this, then you have in this direction, you have sigma yy like that. Okay, so then q, sigma h by sigma equivalent is going to be higher there, and it is going to be lower there, and it can follow any profile. So you will have to calculate q at different points because there is no cumulative value of small q for one specimen. This value can be calculated at every node and the value will be different at every node. Right? So what do we do about it? So you can find out if your point of interest is plastic zone, then, so not like that. Then in your finite element analysis, you can define a plastic zone. You can see where the stresses have crossed plasticity, and there at all the points you will have a variation of Q. Okay, so you can define a parameter by integrating it, by doing an integration over the volume, and that becomes your integrated Q value. Okay, so that is called Weibull triaxiality, not because it has a distribution of Weibull, not because it has a distribution of Weibull, but because it is used in a specific case of brittle fracture where Weibull distribution is used. So in brittle fracture. Okay, any question so far? None.